So this is the first video on tensor analysis. Basically, we'll be talking about tensors. Well, first of all, let's start with basic expression. So if we have this, S equals to A1x1 plus A2x2 plus A3x3 all the way to AN xn. We can view A and X and X as vectors, probably. Can look at them as vectors, right? So we can see that there's a form of linear combination. So if you write this in a compact form, we should be getting something like this: S equal to the sum vi x I from I equals to 1 all the way to n, right? So looking at this, if you look at this expression, basically look at this and look at what we have here. What we can say is the fact that ax, I mean the combination of a1 x1 plus a2 x2 is just the sum of ai xi, where I runs from 1 to n. So, but usually in problems, the summation stops from 1 to n. That's from, that's from 1 to n, where n is 3. 1 to n, where n is 3. Right. So, if we have this, AIXI, let's write this way, it can simply be A1x1 plus A2x2 plus A3x3. So where n, 3 is max, we are ending at 3. So when you write things in this compact form, that's what gives birth to the term Einstein's summation. Now look at this. If you have this AI, okay, yeah, and one thing is this. This I represents obviously the summation from value from 1 to n, right? This I is called the dummy index, and it's allowed to be repeated only once, right? So it can be repeated once. And I mean repeated once. For instance, you have AIXI, right? Yeah, so as we go further, you probably understand why I mean by it can be repeated once. But this is like the first rule we need to understand. It can be repeated once. Now, if we have something like this AI, this, right? What this means in essence is A11 plus A22 plus A33. Hope you can easily see the pattern. So the pattern is the fact that for every I, you replace from where I is equal to 1 to 3, right? Yeah. So A11 plus 22 plus 33. That's the pattern. So if you have this AI, EI, right? It's like let's assume like E are like unit vectors. So it's like E1 plus A2 E2 plus A3 E3. I hope you can easily see the pattern that is developing. So basically that's what the Einstein formation talks about, really. The Einstein summation convention basically is trying to put things in compact form. So rather than writing an expression this way, you can abbreviate it to this, where I is from 1 to 3. Then let's look at the double sum. Double sum, like previously in this example, we had just one sum. We had one sum, which is this here, right? So, but now if we have two, for instance, something like this, I equals to 1, G equals to 1, 3, it's sum to 3, AIG, XI, XJ. Now, I'm deciding not to repeat I equals to 1. Instead of writing I equals to 1, I'm using J instead. It's different dummy index, because for the purpose to make it a unique one. Two, you're not supposed to repeat. I will explain that how that rule comes about basically. So in this problem, I and j are dummy index, and as I said, they can only be repeated once. If you look at this expression, I is here 1, it's repeated once, which is this. J is 1 here, it's repeated once, which is this. Right, so now we want to expand this AI, aij, xi, xj. So in expanding this, what do you do? The first thing is sum over the i's. Then after you sum over the i's, sum over the j's. Yeah, this might be a bit tough for beginners, but hopefully you understand as I solve the problems. So it's either to expand this, you sum over the i's, or then you sum over the j's, or you sum over the j's first, then sum over the i's. Either way it works. So if you have the expression aiji xi xj, now what you do is this. Know full well that I is equal from 1 to can be 1, 2. I is 1, 2, and 3. J is also 1, 2, and 3. So you substitute for the i's first, covering this. Look at this. AI, so instead of I, right, 1j x1 xj, right? Good. Now, if you for the second one, it will be a, instead of I equals to 1, this time the next one should be I equals to 2jx x2 xj plus a3j x3 xj. So what I've just done is simply substituting for the i's by going from 1, 2, and 3. If you remember in this expression, basically what we're trying to do is to provide a compact form of it, right? And the way of providing that compact form, you're reducing this long stream of additional form to just this one. So similarly, in this place, what we've just done, if we replace the i's with 1, 2, and 3. So after the i's, you now look at the j's, but you take it one after the other. With time, when you do this very often, it becomes very straightforward and you understand what you need to do. So you take the first term, this, which is this, a1j x1 xj. This should become a1, j is 1, x1 x1 plus a, looking at this one you're looking at, right? A1 2 x1 x2. So that's for this term. And for this next term, plus a1 3 x1 x3 plus a2 1 x2 x1 plus a2 2 x2 x2. Oh, that's right, yes, plus 8. I'm sorry, plus a 2 3 x3 x3, right? So the next one is this expression, which is a3 1 x3 x1 plus a3 2 x3 x2 plus a3 3 x3 x3. So looking at this very closely now, we've expanded this, and if you look closely, we've gotten 9 terms. So look at the compact form. So if you look at it very closely now, we've written all this in a more compact form, I hope this makes sense. Let me just quickly go through that again. So we have aij xi xj. Let me use a different color this time. So what we did is we sum over the i's first, then sum over the j's next. So for every I, you replace it with, you replace all the I's with ones. So A I J X 1 X J. So you remove this one, these I's to become 1 which is this 3, right? So these are all the I's. Then the sum over the J's, which will replace all these J's with ones. So this become 1. You do this for 1, 2, and 3. We give all these 9 expressions, or 9 terms actually. I hope that makes sense. So similarly, you can do. We have a triple sum. A triple sum basically it's a way of this. So it's the basic expression should be like aij xi xj xk, right? So this yeah, it's usually limited to 3 from I1 J1 K1 3. So if we got 9 terms, a triple sum will be guaranteed to get you 27 terms basically. So how you start is basically I, J, K, X, I, X, J, X, K. So you sum over the I's, sum over the I's, sum over the K's, the J's next. Then you sum over the K's. So, I wouldn't go into the work of expanding this, but basically it's the same principle as that. A, I, J, K, X, I, J, K, right? So basically it's A1, J, K, X1, XJ, XK plus A2, J, K, X2, XJ, XK plus A3, JK. So that's X3, XJ, XK. That's for the I's. Then for the J's, now you simply replace this J now with 1. For this one, you replace this with 1, AJ1, like that. You go over and it gives, then you're able to get all the 27 terms expanded. Well, I'll create a tutorial section to explain, to solve that in details for anyone who cannot get it. But basically, that's the same way it goes through in the expression. Then we've talked about dummy index, basically. And one thing we said is that dummy index can be repeated just once. Now, we also have free index, or multiple, we call them free indices, multiples, right? Yeah. So basically, if you have this, this should start to look familiar to you. 3x3. And if you have this for 2, x1 x1 plus a22 x2 plus a23 x3, and x3 this to give you a31 x1 plus a32 x2 plus a33 x3. Okay, now let me just explain. Basically, if you look at the very first expression we expanded, it looks like this, right? But in this case, we are making like it's more like a linear combination of a's and x's, right? In this case, first of all, one thing I think I did mention that at the first, we write lowercase. Let's assume look at lowercase. Sorry. Lowercase to be vectors and uppercase to be matrices, or to be matrix, right? So if we have like X to be matrix A, this for A, the components of A, like the columns of A, could be in small letters like A, I, J, or A, I. So if you remember from your linear algebra, if you're doing A of X, it's what they call the matrix vector multiplication, And in linear algebra, we can look at things from row. We can look at things by the normal way we multiply. It's the row operations. We multiply a row by a column of the other matrix, right? But also another way we look at things, we look at things from a column perspective. That we look at uh, uh, we look at multiplication to be linear combinations of A being the matrix of the columns of A, right? So that also helps in analysis, right? It makes things a lot easier and makes computation, I think, faster. Yeah. Yeah. So basically, if you look at that, if you look at this, sorry, yeah, we're a bit wandered far apart. Okay, but we're back to what we're looking at. This, we've been able to multiply A11 to give this and this, right? So if, okay, let me just bring this back. Let me repeat this. Okay, so if okay, if we look at this, right, we are this can also be written as A. If you look at all the terms, it can be 1m xm. This can be A2m xm, A3m xm. I mean, the choice of using I, J, K, M, N, O, it's up to you. But the most important thing is you have to follow the summing or the summation convention, basically. But deciding to use them the way you want, it's really, really up to you. I hope that's understood. So basically, looking at this, if you look at this very closely, there's a 1, M repeated. Look at this, M2. So here, the M is 1 to 3, right? Here, M again is also 1 to 3. And here is for this third equation, M is also 1 to 3, basically. So for the free index, that value that doesn't change, look at this 1 doesn't change here, this 2, this 3. Similarly, it's the same 3 here, it's the same 3 here, the same 2 here, the same 2 here, the same 1 here, same 1. The values that I've just highlighted in black are what we call the free index terms, the free index terms, or free indices, right? Because if you look at the equations very well, one unique thing about them is that they appear just once. They appear just once. Dummy index appears twice only, appears just twice, or appears two times only. So basically that's what it is. You look at this. So if you have A1mxm1 or I, so you can think if you use I, it means it consists of this, this, and this, right? So I is the free index, M is the dummy index. So basically that's what it is, right? And that's how the concept follows. So if you have something like this, let's look at rotation vector. Okay, yeah, this IEM. This is a matrix, right? I've written in capital letters, and you see it has two entries here. This is a vector. So it's a matrix vector computation. Yeah, I mean, from those who are still familiar with linear algebra, if you look at it, this and Q, this term Q could be a rotation tensor, right? So it doesn't change the value, but it just rotates it. Anyways, if you look at this, if you have that value and want to expand it, it's the same thing. And then the I goes from 1 to 1 to 3. right? So let me quickly expand this and explain how. Let me explain what it means. We have I here. Let's say I1. This meaning to be QM1EM. Fair enough. Yeah, which will still be equal to Q. Now M should be 1, 2, 3. So it will be 1, 1, E1 plus Q2, 1, E2 plus Q3, 1, E3. That's the expansion. Similarly, if you do this, it goes to Q M2 M2, and you get something very similar to. Yeah, it's okay. Let me just expand that out. Q1 2 E1 plus Q2 2 E2 plus Q3 2 E3, and similarly this will be QM3AM. So QM here will be 1 3 1. E1 Q. Sorry, sometimes it could be a bit confusing, but yeah, this to be 2 3 E2 plus Q3 3 E3. I hope you understand basically what that is. So if you look at it closely with this term, with this means these three values because I is from 1 to 3. Then for each of these terms, if you this term based on this, we have this, right? Then based on the summing convention, we can expand it to this, expand this to this, expand this to this. It's something you should just take your time in expanding, and with time you get used to the summing conventions. In most problems in continuum mechanics, mechanics of solids questions, that's for engineering applications, they usually use this notation to when writing a lot of problems. So if we can, let's recall quickly. We have free index, right? So for instance, Q M I E M. I is the free index, and M is the dummy index. M is dummy index. I hope this makes a lot of sense to you. Now, there are some rules you need to also observe, right? Like for instance, AI equals to BJ. First of all, I and J are dummy, sorry, I and D are free index actually. Free index. Yeah, but this is wrong. This is wrong. And why is it wrong? Because if you have an I here, it should be equal to an I here. So you can write this equal to this, or this equal to this. Because that's will be balanced on both sides, right? Those are the conventions you follow. So you don't write expressions like that. Yeah. So basically, if you also look at it, if you have expressions like this, Ki equals to Ci, yes, this is accepted. If you can see some pattern forming already, the fact that they have to be the dummy index, the free index have to be the same. Similarly, you have AI, BI, CJ, DJ equal to 0. This is tenable as well too, right? You have one here on this part. This is one expression. You have one expression. Then it's here on this expression. And this still holds as well too. These are tenable expressions. So knowing when to use a free index or when something is termed a free index and when it's termed as dummy index could be helpful. But if you have like this is a matrix expression, TIK, and this is fundamentally wrong. It's wrong, right? Exactly. So in the tutorial sections, I'll solve more questions on some problems with this that will give you a better understanding on what to do, basically. So in this, we've quickly gone through a couple of problems on how to use the summing convention and how to expand them. You can pause the video and watch to understand any section you didn't understand clearly. And yes, I'll try to upload the PDFs of all these files too. So in case you need to make reference to any of them, it will be easy for you to see. So one last thing I want to talk about in this short video should be the Kronecker delta. I hope I'm pronouncing that correctly. Kronecker delta, right? So when you look at this, now I guess you probably have seen this delta sign before. So the Kronecker delta is equal to 1. That this will apply if I is equal to j, and it will be 0 if I it's not equal to j. So for these expressions, we have I and j. So anytime I is equal to j, we get 1. This will be 1. Anytime it's not equal to j, we get 0. So what that means is, first of all, remember that for our summing conventions, we'll be using terms, let's say I equals to 1, normally n, right? But this our n, we are limiting it to 3. So if you have this, for instance, it means 1, 2, and 3. I hope this is clear. This is summing convention, right? DII. So what this means is 1 and delta 1, 1 plus delta 2, 2 plus delta 3, 3. And this is equal to 1. How did I know it's equal to 1? Because if you look at this, if I is equal to j, I is equal to j, 1 is equal to 1, of course, equal to j. So this makes, sorry, this makes this 1, this makes this 1, this makes this 1. Sorry, this is not 1. This is 3 actually. Sorry about that. This is 3. Right. So delta 1, 1 is equal to delta 2, 2 equal to delta 3, 3. And that's equal to 1. I think that's actually what's in my mind initially. So then if you have delta 1, 2, if you look at this, if I is not equal to j, this is equal to 0, right? If you have delta 3, 2, 3 is not equal to 2, so this is also equal to 0. So in summary, delta 1, 2, delta 1, 3, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, all of this is equal to 0. Perfect. Yes. So if you have a Kronecker delta matrix like this, Ij, this, now we have a matrix of all of these terms in it, right? So 1, 1, 2, I shouldn't be writing that, right? 2, 1, 3, 1, delta 2, 2, delta 3, 3, 2, 2, there should be 1, 2, 3, delta 3, delta 3, 1, 2. Right. So if we, based on the expressions we've had previously, based on the delta 1, 1 is 0. Oh no, delta 1, 1 is 1, sorry. Delta 2, 1 is 0, 0. Delta 2, 1. Sorry, I think I make a mistake here? Oh yes, I did make a mistake. Delta 1, 2, this should be 1, 2. Okay, yeah, even though they're interchangeable, it's still supposed to, okay, let me just correct it for the purpose of clarity, right? This off, this off. Yeah, it's easy to make a mistake with this. 1, delta 1, 2, delta 1, 3. Okay. This is off too. Okay. Okay. Yeah. Sorry about that. 1, 2, 3, 1, 2, 3, 1, 2, 3, 3, 2. Okay. Sorry. So the right way to look at it is this. Look at this. We have terms of 1, 2, and 3, 1, 2, and 3, 1, 2, and 3. First terms, then 1, 1, 1, 2, 2, 2. Yeah, basically it still follows the idea of summing over i's. Summing over i's. Then when you're done, sum over j's actually. So that's a mistake from my part. What you're supposed to do is to learn how to sum over a particular term and then sum over the next term. That way you write this out without making a mistake. But also, if you notice, some terms are interchangeable, right? Because it depends on the kind of matrix, though, if it's symmetric. But let's leave that for now. So delta 1, 2, 0. Delta 2, 2 is 1. If you look at what we've done previously, delta 3, 3 is 1. The rest are zeros. So if you look at this carefully, this Kronecker delta matrix gives us the identity, or the identity matrix, basically. That's what we get. I hope this makes a lot of sense to you. So if you look at it, if you sum the diagonals, I think that's the trace. If you sum the diagonals, you get 3, which was equal to what we had calculated previously. Right. So if you look at this term, if you have a term like this, let's say 1 m a m, I think, yes, if you have a term like this, you can still view it as this m is equal to 1, 2, 3, right? So 1, let me be 1, 1, a1 plus delta 1, 2, a2 plus delta 1, 3, a3. Now, this, when you have this delta 1 m a m, this is 1. So a times a1 will give you a1. This is 0. This is 0. So delta 1 m a m is equal to a1. Similarly, if you check for 2 m a m, you get a2, and delta 3 m a m, you get a3. But it follows the same way. So rather than writing this, you can still delta I m a m give you ai. I hope this makes sense, basically. So what I have just done is this expression, we have the free variable is 1 here, the dummy is m, right? So in expanding this out, expanding this will obviously give you the sum of terms, right? So m from 1 to 3, so 1 m here, we replace this with 1, 1, replace this with 2, 2, replace this with 3, 3. Based on the Kronecker delta expression, delta 1, 1 is 1, delta 1, 2, or 1 and 1, 3 is equal to 0. I hope this makes a lot of sense to you. Okay. Then finally, okay, you can also verify. I mean, there are lots of expressions to verify, right? They're kind of easy. Delta im and tmj. This gives you ij. You can verify that too. One. Another one you can verify should be delta im delta mj equals to delta ij. Another one should be delta im delta mn and delta nj equals to delta ij. So these expressions, you can write them in maybe your cheat sheet. You can also expand them to prove them out, right? And this is what they will give you, basically. Remember, Tij, capital letters are matrices, then small letters are usually vectors. Yeah. So if you have, like, let's assume you have 3 unit vectors. Let's say you have a vector like this. Oh, sorry. One, two, three, and they're perpendicular or orthogonal to each other, right? So E1, then the expression ei dot ej will give you the Kronecker delta. So, right? So let's assume these are like maybe your unit vectors, and they are perpendicular to each other. So the expression this holds. So basically, this has been an introduction into the Einstein's summation coefficient, convention, basically. So as a form of review, basically, if you have an expression like this, you're simply expanding. If you have an expression like this, you're simply trying to write it in a compact form. So, a compact form. And if you remember from your linear algebra, right, you usually have cases of like ax. Let's say you're multiplying two vectors by the corner, by each side, or so, right? So you're taking one term from here. Let's say a1, a2, a3, x1, x2, x3, right? So a1 times x1, a2 plus times x2, a3 times x3 plus. Now we can get this expression. So writing that in a compact form will yield this, right? So the Einstein's summation basically involves doing that, and we have the concept of dummy variables. They can only be repeated once, like this repeated just once, and also have the concept of free variables that are only once in a particular equation or in a particular side of the equation. Yeah. Then we give examples of when you double them up, when you double sum them, expressions like this, you will typically get 9 terms. All you need to do is to sum over the i's first. Sorry, you sum over the i's first, then sum over the j's first. Then for a triple sum, you sum over the i's, then sum over the j's, and sum over the k's. You typically get 27 terms. If you cannot, I mean, this will take a lot of time to solve, but if you can't solve it, then I'll probably provide a solution or a link to the solution of this. So basically, you get 27 terms if you expand this correctly, right? Yeah. So basically, that's what it is. Then I also give an example like this. If you have, like, let's assume you have a unit vector, you have a unit vector or a vector basically, and you rotate it with a matrix, right? This is like a rotation tensor or an orthogonal tensor, right? Yeah. So to writing out the terms, you can write out the terms basically. So for each I from 1 to 3, you have a value. Then for each one, you expand basically. Then also note some rules. You don't have I equals to bj. No, that doesn't hold. These acceptable expressions. This is also an acceptable expression, right? Right. So this is like a matrix. The moment they must be equal. So it's Tij equals to Tij, right? Yeah. In subsequent lectures, I'll explain something like you can also have this, but if you have something like this, then we are talking of symmetry, basically. Then we have Kronecker delta as well. So for the Kronecker delta, if the I is equal to j, it's 1. If the I is not equal to j, it's 0, right? Then if you sum i's plus, I mean, if you sum, if you have if they are both equal and you sum them, anytime it's repeated like this, that value is a 1. If it's not, it's a 0. Then when you sum this is like the trace of the matrix, right? This is sum of the values on the diagonal. You get that? So, and that's pretty much it. If you have any questions, you can put them in the comment section. Then I'll see I'll see how I can address that. Thanks for watching my very first video on tensor analysis. See you in the next lecture.